Yeah, yeah.
Okay, very good. So this is the streaming microphone. Don't worry. So you won't hear what I say into this microphone. um, it's a really great pleasure to have as a guest today Thomas JENNEWEIN. From, now I need to read because there's so many different affiliations right now that Thomas has, from the IQC at the University of Waterloo, from Keynet, which is a company that Thomas co-founded, and from Simon Fraser University in Vancouver, where Thomas is gradually moving now. So turns out Thomas and I know each other since some time. Thomas did his PhD in both Innsbruck and then eventually in Vienna when Anton moved. Thomas' famous experiments that all of us and many other people know are, of course, the entanglement photon-based quantum cryptography with the famous Venus of Willendorf, which basically is by now physics history. So this was essentially the first actually quantum random number generator. So both of these things were part of Thomas' PhD, and so the rest is history, so to speak. The two of us, together with Rupert, were actually the very first junior scientists here at the Institute when it was founded, and Thomas was my scientific mentor when I started in Anton's group. Because essentially I didn't know anything, and then I was lucky enough to be able to work then with Thomas on his experiments and with JENNEWEIN on the other set of experiments. So thanks for that. Thomas moved on. You spent some time in Australia with an ASC fellowship, and then eventually your first professorship in 2009 in Waterloo. And now, as I said, you're gradually moving over to Vancouver, and I guess we are going to hear the reasons for that. Thomas has won several beautiful awards during his career and founded several companies, so I'm pretty sure he will also tell us something about that. And without further ado, Thomas, stage is yours. Thanks for being here, and well, we enjoy the show.
Thanks. Yeah, thank you. Thank you, Markus, so much for having me. Thanks, everyone, for coming and allowing me to give a little seminar and present our work. And it's very exciting to be back to the Koki Institute and also the university. And it's changed a lot. It's grown a lot. It's just it's really nice. It's great to see all the great work that's happening. So I will talk. I just have a sort of a running title that I use. I'll mostly talk about the satellite experiments, which we're working on, and both to show long-distance quantum communication, but also to work towards a quantum internet. But I do also always like to remember and everyone that ultimately we're putting experiments into space, which were just until recently really basic fundamental physics experiments in the labs. And so a lot of these experiments that we did, like I guess by now it's 20 years ago, QKD experiments over the Danube or you know, around the campus and so on. And at the time, these were like basic, simple, fundamental experiments, and now it's going to space. So I think that's very exciting. And again, a reminder, so it's the year of quantum, right? Where very famous people were even, you know, just talking about, you know, 100 years ago, literally talking about the philosophy of quantum physics, right? And the basic understanding. And like I say, it's exciting to put those kind of fundamental experiments into space. In my lab, in particular at Waterloo University, where I spent a total of 15 years now, I've been working on various levels of technical readiness level, TRL as we call it, for these kind of quantum communication experiments. So starting from very basic fundamental experiments on quantum entanglement and so on, towards more sophisticated systems to do the long-distance quantum channels, up to satellite projects. And I'm actually very proud to mention that with my team, we were already part of several mission studies, and in particular, we are leading a project in Canada called KeySat with the Canadian Space Agency that I'm very proud to say I was the initiator from, and that is now a mission that is being built and implemented, and if it goes well, it will launch later next year. But we've also been part of other experiments, and I'll mention some of them a little bit later, maybe. Yeah. So first QKD. So where do we come from, right? And this is from 1989, the first QKD experiment where they sent attenuated optical signals over 30 centimeters of distance, just as a proof of principle experiment, and that was still led by Charles Bennett himself, right? And the story goes that so him and actually a lot of the co-authors are very theoretically minded people, right? Apparently, he said, yeah, they had this proposal out there in 1984 for QKD, and there wasn't much uptake or enough uptake from experimental groups, so he thought, why don't they do an experiment to show that it works? And that's how this came about. That's the story I heard from him. So I think it's very exciting. But of course, what is exciting is the trajectory from there on, and this is this experiment that Marcus so nicely mentioned, where we did the entanglement experiment. Entanglement produced quantum key distribution. This was done across University of Innsbruck at the Technik campus, and it's actually a really nice example of doing both fundamental physics and applied technology application at the same time. This was actually originally the setup for Gregor Weiss's project in the thesis to do a long-distance bell test with fast-switching analyzers. So we built the systems, we have the modulators, which can do the basis choice, and the basis choice is done with very fast quantum random number generators. So initially that was planned for a bell test and to show that it's been quantum mechanics can violate bell test even if there's fast random switching, and it's so fast that no signal at the speed of light could go from one station to the other, right? And we turned that into a QKD experiment. So by changing the measurements that are done, and also in particular the analysis, we were able to extract some keys which are protected by entanglement, and by investigating the bit error rate, which was in this experiment around 2.5%, we were able to generate several thousand bits of key that were used to encrypt that picture that the Venus of Willendorf, the famous picture of that that little stone figure. And what you can see is Alice's key and Bob's key, which are randomized. They look like random bitmaps, which they are. So what I did is took the random key, which is just a random sequence of zeros and ones, and color encoded a bitmap, and that's so we get those random patterns. But if you look carefully, you can notice that Alice's and Bob's key, the random bit patterns are almost identical. I say almost, I mean they look identical, but we still have a few percent error. And by performing a bitwise XOR operation of the bitmap of this figure, so literally reading out the bit values of the binary file, XOR encoding it with the random key bitmap, we created another seemingly random bitmap, which is called encrypted, is the one in the middle, and when applying Bob's random bitmap on the other side, the original picture will actually come out, because if you apply the XOR, if you apply the XOR of the same bit string twice, it actually cancels out and you get out the image. And so that was very nice. And let's actually,
the original picture, no?
Yeah, this one is for North America, where where we had to black out some features. And it actually, so this was done in the late 90s, and the paper came out in 2000, in the year 2000. And it actually created quite a lot of news. And on the right, you can see a picture from New York Times at the time where the science editor of New York Times picked it up, and it was reported, and it was actually reported in many other news articles around the world. I was just a little PhD student at the time. I remember giving that interview, and for me, that was not even a special occasion. Now I know that talking to New York Times is, actually at the moment it's still a once-in-a-lifetime event for me. But it was very interesting. So, but when I look back and read the whole article, it's actually, there's another page that I don't show. It's actually interesting. Some of the bold claims, they still, stand today. So meaning, there's statements in there, and he quotes me actually saying, "JENNEWEIN said, da da da." Things like, "Yeah, we've demonstrated this system, and it's almost ready to use. Can be commercially, could be turned into a commercial system, da da da." So if I read this now, interestingly, a lot of those statements are still correct today, where we still have great prototypes and they're ready to be commercially deployed. And so QKD has evolved a lot, and a lot has been, a lot more has been advanced, but it's still not quite mainstream, I think, the technology, right? But we're working on it. The other thing that came out, which ties more into where I'm trying to go next, is we were invited by this computer magazine CT, which I'm very glad to notice it's still around, I believe, right? So that's really cool. I was a huge fan at the time of everything in CT, and I was really excited. They invited us to write a review article about this QKD, and I actually spearheaded this article together with Gregor and Anton, and it's a several pages review of, it's really, actually, I actually forgot about it until recently when I dug it up again and read it. It's actually a really nice review, but it's in German. But what's interesting is in the introduction, it outlines, the story is about an outline of a quantum internet. And it talks about financial, transactions across the Atlantic, and they want to talk, there's a bank in Frankfurt wants to talk to a bank in New York, and they want to exchange, and to get a secure transmission, they just grab the latest keys from their quantum internet, right? Something like that. So what is interesting that after so many years of, and so, literally 20 years later, I've now sort of started to try to go back to this ultimate vision of building a quantum internet, and after spending a lot of time just trying to work out just to get the long distance channel going. So I'll get back to that later. In my Waterloo lab, so like I said, we try to expand the distances, in particular in free space. And one of the first projects we did is so there was this Innsbruck experiment here, and you see myself standing at the source actually. I was in a boiler room, which was thermally very stable. Unfortunately, it was like 30 degree, similar to what we have now, but it was very stable. We did an experiment on a pickup truck, actually, with moving systems. So that was one of our first experiments in Waterloo in regards of outdoor. So we designed and built all of these tracking systems required so that a telescope on the building and could pick up or connect this to a telescope on the back of this truck. And while the truck was driving, we were able to establish keys. And we later put more advanced prototypes onto an airplane. In 2017, we showed our QKD from ground to an airplane. And again, we designed and built all of the tracking systems as well that I needed. And but what is more important for that airplane experiment, we also used payload prototype that we developed for our satellite mission. So it wasn't space hardware as such, but it was space or flight-like hardware. And because a lot of my time and effort went into showing that this technology has what they call a path to flight. And so what it means is we try to use components or elements or parts which it's known to be able to put into space, right? What I mean is we can't make a system that needs a huge power source or a huge computer to operate, right? So that was a major, Oh, and maybe you might ask, where's the plane? Actually, you can see that streak on the sky. That's the airplane in a 10-second exposure as it's moving along. So it was about 15 kilometers away. So why are we interested in satellites? The motivation boils down to covering large distance. I think that's the main motivator. On any ground channel, the link losses will be exponential with the distance. And there's a very simple reason. If for a unit distance, you have the same probability of scattering or losing the photons, if you integrate over the channel, you end up with an exponential decay. In free space, that's different. Apart from atmospheric scattering, but once you're in vacuum, like in outer space, the only loss mechanism is the spreading of the beam. So any optical beam that starts with a certain diameter will experience a divergence. One can also see it as like diffraction, kind of, right? And but as such, the transmission loss will then scale quadratic with the distance. I mean, there's also lambda and the diameters of the receiver and the transmitter that matter, but the scaling, which is maybe the most important part, which is set in this equation here, is going to be quadratic, right? So that means suddenly you have a major gain or advantage over the exponential scaling when it comes to large distances. And for example, we did lots of studies, actually including a study we ran here in Vienna. Marcus was leading it, actually, the early ESA studies. And we still actually have some very nice study papers about entanglement in space, from which a lot of those ideas actually came from, right, for quantum and entanglement experiments in space. And at least on paper, sending entangled photons between Earth and Moon, or even Earth and Mars, is actually doable with today's technology, with today's telescope. It's in principle possible. I'm not advocating for it at all. It would be still cost a lot of money. There would be a lot of technical risk. But I still think it's interesting that at least on paper it could work. So and I'll say a little bit more about that. We've been part of a project, for example, to do a study on entanglement distribution across the Atlantic. And yeah, while I say it's doable with today's technology, it is actually still pretty difficult to do, right? So, but it is interesting. Another reason why satellites are relevant is that, even if we, one day have very highly operational fiber optic based quantum repeaters and so on, there will still be a use case for a satellite to ground link for quantum, because there will be locations on ground where there is just no infrastructure, right? And for example, in Canada, that's a big topic. That's why Canada has a big interest as well. Is if you look at the map, or not the map, this picture of the Earth, there's all of this northern area, which goes all the way to the Arctic, of course, which is very, very sparsely developed in terms of infrastructure. Many places are only accessible by airplane and so on, and yet Canada has to operate and protect all of those northern areas, and that's another interest of doing this long-distance quantum communication with satellites. I already alluded to the foundational physics aspect. So early on in our satellite mission that we studied in Canada, we actually got together with a whole group of theorists at the Perimeter Institute, which is also based in Waterloo. This was around 2010, 2011, and we came out into a very nice review paper in 2012, where we sort of reviewed all of the various science experiments one could do with long-distance quantum entanglement in space. My biggest interest, and I pushed really hard in those brainstorming meetings, was finding an interplay of quantum mechanics and relativity or gravity. Can we do something with entangled photons over long distance? And can we see some kind of, what kind of gravitational effects can we see? Unfortunately, well, okay, first, the good news is, and in the paper there's also a list of all those effects. There's lots of various effects that can show interplay between relativity and quantum, or I guess optical fields. But the unfortunate part is those effects are all very, very small, right? So they're well below what it can be measured. I got people to work out, for example, the Earth is rotating. So if you send photons horizontally on the Earth's surface versus if you go east-west or north-south, you should see a slight polarization shift because of the rotation of the frame. Okay? So yeah, that was very exciting. So then I asked them, yeah, and can we look at numbers and so on? They got back to me at some point. It was like 10 to the minus 20 is sort of, roughly the polarization rotation that you could get, right? Or something like that. It's just, unfortunately, way beyond what can be measured, right? And there was many other such examples that we looked at. Another effect, really interesting, would be accelerated reference frames, where you can get the Unruh radiation and so on, right? But anyway, not just out of scope. But what is interesting is still that vision that what I was trying to do in this picture here, which was the motivation for this discussion, is, well, if we think of human technology, right? On the left, I had this bar. We can, human technology can maybe cover the solar system. I think that's reasonable, a reasonable statement, right? We have sent probes that far. And, with today's technology, we can go maybe Earth, Moon for entanglement, and future technology, we could consider, solar system type of distances. What can we do, right? And what kind of distances and velocities, in particular relative velocities, could we explore? So that was a very interesting premise. And what I don't want to say too much more. One more thing I'll mention is, I think we should still keep this in mind, all of us, because if you think of the Earth, the size of the Earth, right, as the ultimate, so if we have a ground-based entanglement distribution, let's say we have very fancy optical fibers or repeaters which can go Earth's diameter, so that's 13,000 kilometers. So if you think of the scale of, things in the universe, that's actually still nothing, right? So what if entanglement, we have to push the distances for entanglement further. I think there's a case for that. And another small comment I'd like to make is there was a revamp of such a study done as part of the Deep Space Quantum Lab, Deep Space Quantum Link project initiated by Makan Mohageg and Paul Kwiat in the US out of JPL. They put together a study team with international partners, and I was fortunate to be one of those study partners. And we revisited a lot of these basic fundamental physics questions and redid there's a new review paper now, or newer revised review of these scientific experiments. And there is one of the proposals that emerged was to study a phase type interference, a large interferometer with which is like a phase encoding, and that could allow to study the interplay of gravitationally induced phase shift on the quantum interference. And that's still, I think, that was going to be the proposal, but I believe NASA didn't really pick up on this deep space quantum link. Nevertheless, the ideas are out there. For QKD, the case for QKD, so now switching back to the application, is the following. So what is the likelihood that a quantum computer can hack a RSA key, right? RSA being that algorithm that is used for public key encryption, like we use on our internet today. And Michele Mosca with Evolution Q, their startup, they did a study on, by surveying experts in the field of cryptography, but also quantum computing. And roughly, so the latest update was 2022. Roughly, they determined that within 10, 15 years, the respondent would say there's a 50% chance that a quantum computer will be able to hack such a 2,000-bit key. That was the kind of question. So now, what does it mean? It means, well, today we don't really have to worry in some sense. However, if you're sending information or data over the internet that you want to have secure for 20 years, or 15 years actually, then you have to start to worry. So if you're like a major business or a corporation or a government, then you have to worry now, because most likely what you're sending now might be relevant in that time frame, right? So that is the problem of quantum computing. So already now there's a push to try to create awareness for that problem and switch to post-quantum algorithms, and some of you may have heard of that already, or use QKD, quantum key distribution, as one of the workarounds for that problem. So, of course, I'm an advocate of using quantum key distribution. Oh yeah, I also like to mention this protocol that we developed, and I have to give full credit to Daniel Gottesman, who was the mastermind behind this protocol, which appeared in 2012. It's about enhancing interferometric telescopes for large baseline interferometry using quantum repeaters. And so why is this relevant? Well, many of you would have noticed a few years back there was this it was big in the news, where with microwave, so radio telescopes, they were able to take or reproduce pictures of black holes, showing this amazing feature, right, of the halo around them and the eye of the black hole, right? So very fascinating. They did that by combining the data from radio telescopes around the Earth, and combining the data coherently and effectively getting a very high resolution, because the effective aperture is the size of the Earth, essentially. So if we could do that with optical telescopes, so that was in the microwave domain, right? So if we could do that with optical telescopes, this would, for example, allow us to image exoplanets, to literally look at an exoplanet, for instance, right? Or just enhance the resolution dramatically. But the problem is how to do optically. One can't do the same tricks as radio telescopes, because optically one cannot record the data, the oscillation of the field directly, right? And so that's a challenge. So, however, what this protocol now proposes in this 2012 paper is that one can actually, so rather than bringing the signals together to do interferometry, one can actually distribute entangled states to the telescope stations and take correlation data measurements, and then based on those correlation measurements, one can reconstruct the same interferometric visibility scan as one would in a regular sort of interferometric measurement. And what is striking is that one can show that and that's the important part of this sensing protocol, it's a sensing protocol, that the sensitivity with the photons coming from space scales exactly the same as if it was a single photon measurement by bringing the signals together and interfering them. So I think that's the important part. However, one could have a quantum repeater, which is fully error corrected, to share and send out this entanglement resource. And if it's a proper repeater, right, it will be deterministic and high quality. And so one could effectively connect telescopes over large distances. So that's the hope. So this protocol has been around for a while. You can see it's from 2012, but it has now picked up quite a lot of interest. There's many different protocols that have been, developed since, inspired by this paper, and also some experiments recently. And also in my group, we just recently came out with some new studies on trying to find, what are the optimal states one could distribute, if it's an all-photonic scheme and so on. So it's very interesting. But I have to admit, there's still a long way before astronomers will actually switch to this method. But I do believe that for quantum networks and quantum repeaters, this is an interesting use case because it's like this small-scale, noisy quantum computers, which are not full-fledged quantum computers. They can still do something interesting and useful. So I think this might be an application for the smaller scale, not so good repeaters. They can maybe not do the full-fledged repeater protocol, but maybe they can be used for a quantum telescope application. So I do believe that for repeaters, it's definitely an interesting direction to keep working on. And I just wanted to check the time actually, because I realize they're talking a lot, and I haven't even really spoken about our lab results. I'll get to that. We've been looking at various. So switching now back to my original theme, which is this long-distance satellite experiments. Just recently, we did a study, like a white paper on trying to take a fresh look at if we want to do entanglement, let's say across Canada, what kind of links or scenarios do we want to consider? And we looked at various like satellite altitudes, starting from LEO, low Earth orbit, until up to GEO, and even highly elliptical satellites. And we also looked at high altitude platforms. I think that's a very promising platform. And we try to chart out where can we do a useful link. And in this kind of plot here, we have the link loss on the x-axis and the time it takes to distribute a useful amount of entanglement on the vertical axis. And we shaded off those scenarios where there's just not enough data rate to do anything useful. And it turns out that just based on this simple classification, only a few scenarios are useful. Mostly it's a so-called downlink, but also there's a few of the blue symbols you can see, right, which are links between systems that could be useful. And so that helps us decide which direction to go next. And I will point out that, and this will be important for us when talking about really very long distance, that multi-satellite or multi-station solutions will most likely be needed, where we essentially have relays. Okay. And why does it? Okay. Let me just very briefly introduce you to the first Canadian satellite. It's called KeySat, Quantum Encryption and Science Satellite. That is first technology demonstrator, which will not be able to distribute entanglement across Canada, but it will allow us to distribute quantum communication or quantum entanglement from ground to space. And so on the right, you can see a CAD rendering of the satellite. It's over 100 kilograms in mass. You can see the main feature. It's our 20 centimeter telescope that will act as receiver and but also as a transmitter for quantum signals. And with that, we'll be able to do an uplink of signals, but also a downlink. We have also identified various partners across Canada who will participate in the project, but I will say, most importantly, at Waterloo University, which is this little red mark, star symbol on the right bottom of that map, that's where we have the main science operating center, where we do the mission planning and mission operations, or I should say the payload operations, and we'll also have a ground station to operate the system. In order to do this in space, we had to do studies, let's say, on the atmospheric transmission, and for example, how to choose even which wavelengths to use. And I actually won't go into details, but we really try to take a bottoms-up approach and go to that with an open mind. Yet what we determined is that 785 nanometer was kind of an optimum for us, so that's the one we chose. Here's a few more pictures about the systems we built. The payload prototypes tested on the airplane. You can see the Twin Otter aircraft of the NRC, the National Research Council in Ottawa. On the right, you can see a detector module. It's actually in a thermal vacuum chamber, which we had, they're custom detectors that we designed and built together with industry, I should say. And we did also radiation testing with those, because one problem of putting photon detectors into space is that they're very susceptible to proton radiation. And so once they're in space, they'll pick up a lot of dark counts and get very bad very quickly, right? So these are very nice detectors, and you put them into space, and after a few weeks even, they'll have very bad dark counts. So we have to cool them. We have to do annealing, and so it's quite a big effort to get this to work. And here's an actual experiment where there's actual now detectors in space. We were fortunate enough to be a part of this mission called SEEK. It was spearheaded by Paul Kwiat in University of Illinois, and with various partners, including us in Waterloo. And so we provided that detector module that you can see here on the left with 4 silicon detectors provided to us by Excellidas, which it's the same detector as in the regular SPCM modules. And we built this electronics and all space grade. And and now it's flying on board. It's on the outside of the ISS. It was launched November last year. Inside of you can see the experimental system and box. And it's already producing entanglement data in space. And also a big part of this is testing the viability of the systems in space, including those dark counts that I mentioned. And so those detectors experienced a lot of degradation already, even though the radiation at ISS is relatively low compared to other satellites. And right now they're running annealing experiments, including laser annealing. So it's really cool. By sending an up to 1 watt laser on those APDs, which sounds totally weird because you have those single photon detectors, but by sending a 1 watt laser for a short time, like a minute or so, one can heal quite a lot of the dark counts. That's the hope. We've done ground experiments a few years back with radiation damage detectors, and it was very promising, and now they're trying to replicate that in space. If that works, that could be a really important piece for future satellite missions for quantum technology, where one can try to improve the detector degradation in space. So it's ongoing. Please stay tuned.
The astronauts are doing that.
No, it's all remote controlled.
Okay.
Yeah, thanks for asking. Astronauts, I think they only handled it for the installation process. But because it came up in a Dragon module inside, and then it had to go outside. But it's installed on the outside of the ISS. And what's very interesting, I think the plan is to, or at least there's a potential plan to bring it back to ground. And that would also be very interesting, because so it would allow to do a lot of troubleshooting of components, and there's been some fault, some behavior that needs investigation, and so it's actually very interesting. Which would be not possible without the satellites. So ISS offers that opportunity. We'll see. Yeah, I think I'll skip that. And this one, just one more thing I'd like to point out is, so we're looking at the, so what I said, one of the features of our system is it can be a receiver. It also has a QKD source, but I didn't want to, I skipped that in the sake of time. But one benefit of doing the uplink is we can envision scenarios where we have an entangled source on the ground at a ground station, and when the satellite is flying overhead, which is just a few minutes a day, one could make a network of sending entangled photons to multiple users on the ground and linking them up to the satellite. So that's the long distance component. And in this paper here, which appeared in EPJ last year, we worked out the details for a 4-to-1 network, of entanglement distribution between the ground nodes and the satellite. But then the same system can be reconfigured to a multi-party network on the ground when the satellite is not available. For the 23 hours, 54 minutes of the day where the satellite is not available, the network the users can do pairwise interconnectivity. So that's an interesting aspect that I think is very, very unique to this uplink, because I get that asked a lot. Why even is the quantum uplink interesting? And one side bonus outcome of all of these studies was we also modeled the difference between bucket detector and photon number resolving detector, because when doing entanglement-based QKD with SPDC, there's always this kind of problem with the multi-emissions, the multi-pair emissions, right? And I myself thought that, well, if we only had bucket detectors, we could, distinguish the multi-pair emission from the single-pair emission, and then therefore have a better QKD. But it turns out there's actually virtually no advantage of number resolving detectors versus bucket detector. And and I first actually I had multiple students in the lab actually simulate that independently because I didn't believe it, but now I have an understanding why. But I can discuss separately. But I thought it's interesting because people spend a lot of time and effort building number resolving detectors, versus the standard bucket detector. And unfortunately, this use case is not one of the ones we need them for, I think. Yeah. I'm happy to discuss more about that if somebody's interested. And lastly, I just wanted to present, just really quick, because that's a big sort of favorite topic of mine, is alternative encoding of quantum information for free space. So in all of those long distance experiments that I mentioned in free space, we use polarization encoding, and including also, it's not just us, it's virtually every other group or other experiments for long distance quantum communication have been polarization based. It is sort of softening now. So one direction we looked at was time bin encoding in free space, and the big challenge of time bin encoding is that those two time bins that come at a time delay, and in order to analyze them, one has to build an interferometer that can interfere the early and the late pulse with each other, right? That's needed to measure the superposition stage or state. However, the problem is that a regular interferometer will experience, if the beams are multimode, like a free space beam, they have a lot of aberration, they are multimode, they will experience a mode mismatch. The long and the short arm will have more evolution, essentially, undergo more evolution because it's a longer path, and that will mess up the interference. And so we explored over the past, by now it's also 10 years already, various interferometer designs which can overcome that problem just passively. And the simplest way to see it is to think of having relay lenses in, so here's a picture of a Michelson interferometer, and we have relay lenses on the, in the long arm, which essentially create an image of, let's say here, with a plane which we call, let's say, the virtual mirror, and it's like a 4F imager, right? It comes back and it's re-imaged at that plane. If you do that, this is sort of kind of known as a virtual mirror, then the field here looks the same as it does on the short arm at the mirror. So as a result, when the beams come together, they interfere perfectly, right? Or very well. And so one can even get very high interference quality with a totally multimode beam. There's several different versions of this. Relay optics, we've also done curved mirrors and those delay cavities, and there's many different incarnations. Another way to do it is to use just literally glass. So you have, in the short and the long arm, you have different refractive indices. That can also do the trick if they are chosen right. So it's actually very interesting. What is a little bit embarrassing, we actually rediscovered those methods painfully and over years of thinking about it. And then we sent in our paper for review, and then it came back as, yeah, but what do you want? This has been around forever in laser Doppler systems, where they call, it is known as a field-widened interferometer. And I literally could not find that word because I didn't know what the search term was. And who would have thought it's called field-widened interferometer? Anyway, once I knew that in the community it's called field-widened interferometer, suddenly I found all those papers going back to the 60s, talking about those kind of interference tricks. Astronomers use it for white light interferometry. For example, there's one method for detecting exoplanets by looking at motion of a star, because when the planets circle around, they will move back and forth, and they do white light interferometry to detect that motion. And so astronomers have been using those kind of interferometers for a while to do white light interferometers with a path difference to detect that phase change. So anyway, once we figured that out, we were able to do a couple of time bin experiments over free space. Oh, I don't have a picture about, yeah, we did a QKD over a kilometer of free space. More recently, we did a QKD with time bin over a multimode fiber, I should say. So this was a regular multimode fiber, 2,000 modes, very ugly beam, but we're able to get full visibility on the time bins. And also what we incorporated here is what we call a reference frame independent protocol. So I won't have time to go into that, but essentially this protocol is like a tomographic type of QKD. So we just measure the purity of the state, and as long as the phase, so for time bin it means we measure the purity of the superposition state, but we don't have to know the phase. As long as the phase does not drift too fast, we can still determine the security. So then what it allows us to do is to do a time bin QKD, where you have Alice and Bob, and they both have interferometers, without having to synchronize the interferometers. So it's really what we call reference frame independent. So I think it's very exciting. And now the latest thing, and this will be, it has to be my last slide. And the latest direction we're exploring is frequency bin for free space. So frequency bin has actually also been around a long time, and in particular in fiber optic system, it's very popular because the way to create and detect frequency bin in telecom systems is actually relatively straightforward, right? If you send a signal through an EOM, you will get the sidebands, and that's kind of like your frequency bins, right? Or if you want to detect your frequency bins, you can use electro-optic modulators to mix up the different frequency components. So we've been looking at that in the context of satellites and also in free space. I'll get to that in a moment. But however, there's a slight problem, and we outlined that in our paper that we put up on the archive late last year. That it turns out, though, there's a problem with frequency bin. It is directly susceptible to path length change, and so while time bin and polarization polarization doesn't actually care about the path length variation. Time bin is only susceptible to the change to the variation of the range. So even for a satellite, that's not too bad. It can be managed. However, frequency bin is directly proportional to so the phase in the frequency bin is directly proportional to the path difference. So suddenly, the phase change we get is really high. And we looked at some numbers, and we expect a phase drift of 10 to the 5 pi or something, or radians, I should say, per second, just from the relative motion. So it's going to be a challenge. So that was a bit of a setback for our aspirations, because we were working with on experiments already. Actually, this is part of a EU Horizon project with various colleagues also in Europe on studying frequency bin entanglement sources and studying frequency bin channels. So it was a bit of a setback. However, we left it open as a question of maybe that can be solved with very careful reference signals to undo that modulation. But what we were able to show is that we can use our same interferometers with relay optics to analyze frequency bins, it turns out. And we did an example. A first example experiment. We create just 2 frequency lines. We took a very narrow laser, sent it through an acousto-optic modulator to get the laser and the first fundamental diffraction, right? So that's our frequency. Those are our frequency bins. And we were able to send it through a multimode fiber and still get a very good analysis of the frequency bin. And essentially the idea is that this interferometer, because it has different path length, we can split the frequencies according to the asymmetry of the interferometer matches the frequency splitting, I should say, and so it can be used as a set measurement of the frequency bins. So that overall it worked, and we were able to show that we can even for this ugly beam, we can still measure the frequency bins. And this is now, more importantly, still work in progress, but so more importantly, we were able to show it now for actual quantum signals. So we worked with colleagues in Pavia who have a frequency bin entangled source, and we were able to use our compensated interferometers to show we can actually detect and measure these frequency bin entangled photons using our interferometers and analyze the signals without actually needing active modulators. It's just passive, just using time detection and those kind of interferometers. So yeah, that's not published yet, but it's very close to come out, so be coming out. Okay, and yeah, I just like shamelessly make a little bit of self-advertisement for our startup, KeyNet. So KeyNet is a small company in Waterloo, which set out to take the ideas around our satellite mission, but rather than work on a fancy, full-fledged sort of scientific demonstrator, we're trying to, in our startup, build a minimum viable system. So just good enough to do a QKD with a satellite, and there's a small prototype that was built. It's a very shoebox-sized payload, which can be installed on a satellite. It's very small, very low cost. And actually, there's an announcement. We received funding from the space agency for a space demo, so that will be launched, if it goes well, next year as well, for a test of that payload in space. Yeah, and I'll end with this one. So for me, the future is the quantum internet with satellites. So I mentioned, as also Marco said at the beginning, I'm starting a new lab in Vancouver at the Simon Fraser University. And in particular, one of the motivations was to collaborate very closely with the group of Stephanie Simmons and also Daniel Higginbottom, working on quantum processors, which have very good optical interface properties. So the idea is to use those quantum processors as memories and part of a quantum repeater in a network, and to make a connectivity for very long distance entanglement. And the hope is that this will allow us to eventually do entanglement distribution over large distances across Canada is the goal. And that's coined as the next generation satellite, which we called KeySat 2.0, which the mission, the pitch for the mission is we want to do quantum teleportation across Canada. And I will have to say, though, I got a lot of inspiration of those kind of statements from working many years here in Vienna with Anton. So, yeah, but of course, seriously, we do think it's a very viable or very valid goal, because by being able to demonstrate this teleportation, we have to work out a lot of things that are needed for a quantum internet. We have to interface to memories. We have to perform Bell state measurements to do entanglement swapping. And those are all important schemes that are required to get closer to that vision of the quantum internet. So I think I'll leave it there. I want to thank you for your attention, for having me, and for sticking around in these temperatures. Yeah, thanks a lot. Yeah, thanks.
Thanks so much, Thomas, for this fantastic insights into all this
Yeah.
work. Questions? Shoot.
So on top of radiation effects on when you operate your detectors, is there any other consideration that you take regarding the operation of detectors? Let's say cooling the detectors, is it hard? How do you handle with space environments?
Yeah, so we have to cool a lot. We are cooling to -80, and the goal is even colder than that, Celsius. And so in space can be done. It's just a matter of careful thermal design and yeah, but it can be done, right? We wouldn't want to cool that much if we wouldn't have to, but unfortunately, we did radiation testing at accelerator in Vancouver, called Triumph, and it just showed that the radiation is so bad, so unless we cool down so much, we won't be able to have a workable dark count level. And then on top of that, we will do thermal annealing every once in a while, meaning it will be likely every 1 or 2 months. But we'll wait until the dark counts have risen too much, and then we'll run annealing. Annealing means we heat it up to close to 100 plus for like an hour, and after that time, the dark counts have dropped on the order of 1 order of magnitude. So yeah, a lot of analysis and engineering went exactly into that system and try to get it right. It's always a function of temperature, and the Seek detectors are not so cold because they didn't have, they had restrictions on energy and so on they can use, but they went from, in the lab a few hundred, so around 0 degree. I don't know the exact number now. They would go in the lab, maybe a few hundred dark counts per second, and they go up to tens of thousands. So right away, yeah. Those were passive quenched, yeah. Yeah, yeah, yeah. I spent a lot of time thinking about that, and so the main reason is electronic safety. So passive quench is, of course, much slower, but it's extremely fail-safe because there's only you have a high voltage bias, like a source, and you have those resistors, and the quench resistor is relatively large. So it also protects the diodes. So even if there was, major light influx or something, it's very unlikely to burn anything because the diode protects it. And yeah, those diodes have around 300 volts, something like that. Yeah, 280, 300. Yeah, yeah. So we operate like 20 to 30 volts above breakdown. Oh, the laser annealing is not really known how it works. So laser annealing, and there's also papers. This was spearheaded by Vadim Makarov, I should say, in Waterloo, but my group was part of those experiments. So they did very careful measurement of the diode temperature while the laser is lasing. And the readings were that the laser was, even though there was a 1 watt, they went actually to 3 or 4 watts in the end. The laser only heats up to 35 degrees or something, physical temperature. Yet the dark counts get drastically reduced, and before the diode obliterates itself. So it's all in that paper. They have nice pictures of increasing the power, and at some point the window gets foggy, and then you start getting solder balls forming. So there must be more going on than just thermal. There must also be some kind of deep charge, I don't know, flooding with charges or clearing out the charges happening with that laser illumination. We did some studies on that. We try to investigate laser annealing by comparing what if you have a certain average power, or what if you do like an on-off, so you have the same average power, but like a pulse width modulation, but you have like an on-high and a zero in between. And it was not really conclusive, but it did seem that the total energy that's deposited is what matters. Yeah. No. What I mean is, it's going to be like it is today with normal communication. I mean, pretty much all our internet traffic is fiber optic based. Yet there is still a lot of satellite communication technology that's still being developed, actually, right, for internet over satellites. So that's what I meant. There will be some hybrid solution in the end. That's what I'm trying to say. Yeah. No, interestingly, there are schemes to do some kind of photon heralding, which, at least in principle, could overcome the losses. So yeah, you're right. If you do direct transmission and you detect, I think there's no way around the detection losses. But there's more complex schemes where you essentially verify that a photon arrived and only use those cases and so on. So there's been nice proposals and experimental data sets for that, or coupling to memories, right? Which is what all of the DI-QKD experiments have shown, right? They've either at atoms or at other NV centers, right, where they use the photonic channels to establish the entanglement, and once they know the entanglement is there, then they run the experiment, which could also be mitigated, established via satellites. And yeah.
On your slide with the satellite being on or off, there was, so during the on experiment you had the like n to 1 connection, versus in the off you could have a, I guess, a peer-to-peer essentially is the idea, where so in the off scenario you would have somebody linking up to the satellite and then back down on the other side once the pass goes over the other party, right?
Yeah.
And in the on scenario, the end users to the satellite, is that like an idea, like, I don't know, something like conference key ring or something like this? And does it mean that all need to have a line of sight at the same
You mean
time
like, no, this means there's only one ground station, and the users would be connected via optical fiber to that ground station. And the other feature is, and maybe I wasn't clear about that. The users each get entanglement between the satellite. So the entangled photons are multiplexed, so that one user connects with the satellite, the other user connects with the satellite. But it's not like a conference type of key or multi-user key. It's really multiplexed entanglement. So they can.
But you said the users need to be connected to each other by fiber.
Well, they have to be connected to the ground station. So the idea is at the ground or near the ground station, there'd be a source of entanglement, and the users would connect to that ground station. And then the goal of the satellite is, because if you want to, let's say here we have this hypothetical scheme. There's Waterloo and Montreal, and there's users in both cities, and they want to interface with each other, but also across the different networks. And one way to do that is to use the satellite as a trusted node. So by establishing the entanglement of the users to a certain key on the satellite will carry that across as a trusted node, but it will be, in this case, the satellite would have 4 separate keys for each of the users. And then it can be used with the other users at in this case, the Montreal station. And then on the satellite could then do the XOR operation between the different sets of keys to establish some key between, whichever users want to have a key from the Waterloo and the Montreal side.
And this can be achieved in a purely uplink scenario as well.
Yeah, it's uplink, yeah, and it happens at the same time, yeah. Okay, yeah. Okay.
Just about APDs, you said it's from Excelitas, so you always use them even for the thermal annealing and the laser annealing. You just buy them directly and there is no in-between work inside the house.
The APDs themselves, we bought as a component, yeah. But we built the electronics and stuff around it. And we also did test other ones as well, not just Excelitas.
But they are working best.
Yeah.
But now when it's on the ISS, so you wait for the degradation to happen, and then you perform the process of shooting a laser. Did this happen like over some periods, like then it degrades again, and then you can fix it again?
Yeah, we've done a study on the ground with the cyclotron tests to show that we can do repeated annealing. We've done that, but not in space. And now that's happening in space. Yeah, and it's literally happening these days. That they have already turned on the laser, but they didn't quite reach the full power. But they're literally doing it, these days. Yeah.
But even on Earth, you could come back to the same point. It's not like
not quite the same point, but you can get at least close. What we did is we had detectors which were radiated with protons. The dark counts went up, and then the laser annealing came later, and it showed that the dark counts can go down quite a bit. It never goes back all the way. You can actually never get that, but it does improve quite a lot. Yeah. Okay. Thank you. Thank you for having me.